So far we have only talked about misclassification rate as a measure of error, and equally we could talk about accuracy, which is 1 minus the misclassification rate, as a measure of how good our model is doing. But in fact there are many types of errors which I want to introduce in a second, and it's really important to understand them and their differences. Those type of errors we will discuss about now are important for any type of classification problem, not just logistic regression, but the same ideas apply also to really any other model of classification. So just to give you one quick example, what is kind of wrong with accuracy or misclassification rate. Imagine I come to you and say, look, I have built a machine learning model which produces a spam filter which is 99% accurate. You say, well, great, you did a really good job in building this excellent spam classifier. The only thing you do not know is that actually only 1 in every 100 emails is a spam email in my example here. And in this case, so we have that actually if I build a spam filter which says there doesn't exist any spam, every email is classified as non-spam, it will be correct in 99% of the cases, and 1% of the cases it's wrong. So it's accurate 99% of the cases. But I mean, as you can see, it's a kind of very silly model. There's nothing smart about it. So it's not really good, and it would be it's kind of deceiving to say that it's 99% accurate, even though it's correct. And this might seem like a contrived example, but I've seen a lot of cases like this on the internet where people speak about some great classifiers they built, but in fact they aren't actually at all that good. The complication here arises because in this case classes are not balanced. There are many more emails which are non-spam than there are emails which are spam, so that makes the whole thing a bit more difficult to investigate. The same is true for many diseases. For example, I look at cancer. Obviously in a general sample of patients, the fraction of patients with cancer will be much smaller. So I will get a very good misclassification, a very good accuracy if I just said no one has cancer. I'm probably right in 99.9% of the cases, but when I'm wrong, I'm really, really wrong. So this is why we have to look a little bit at different error types, because they help us in those cases, especially when I have imbalanced classes. So one way of summarizing some of the different error types is this matrix here, which you can see on the top right, which is called the confusion matrix. So let's just look here at all the different cases which are actually of class 1. So this true 1 or true positive are the cases which actually in reality were of class 1, the students which actually passed the exam. And here are the true the true zeros, so the ones which actually failed. Now I built a model, and my model can make prediction. My model can say, I predict class 1, I predict a student to pass, or I predict class 0, I predict a student to fail. But obviously, as we saw already, not everything does the model get correct. So in some cases, I predicted to pass, and the student actually passed. In other cases, I predict the student to fail, and the student actually failed. In those cases, I got it correct. So in a sense, those terms on the diagonal here were the cases when I got it correct, whereas the ones in the off diagonal were the ones when I did it wrong here. For example, I predicted the student to pass, but in reality the student failed. So let's just look and kind of make sure we understand those concepts. So here I have the students which passed and which were actually predicted to pass. Those ones here, those are just this one here, this one, this. Those are all the students which I predicted to pass and which actually passed. Now there are some students here which kind of, I predicted to pass, but they actually didn't pass. This is this one here. And those are sometimes also called the false positives. So the green ones here are the true positives. Those are also ones which I predicted to pass and which actually passed. Now there are some which I got wrong. I predicted them to pass, but they actually didn't pass, which is this one orange one. Now I obviously have all the ones which I predicted to fail and which actually failed. Those are the true negatives, and those are those ones here. Those are all the ones which I predicted to fail and which actually failed. And then were the ones which I predicted to fail, but which actually passed. Those are those two here. So those are all the different errors. These are the false negative here, just for you to see the different error types. So I have the true positive marked in green, which are the ones predicted to pass and which actually passed. The true negatives are marked in red, which are the ones which were predicted to fail and which actually failed. And then I got the ones which I got wrong, which are the false positive, which are the ones which were predicted to pass but in reality failed, and vice versa, the false negative, which were the ones which were predicted to fail but actually passed, which are marked in yellow here. So if you count them, you should get something like, so the first one here are the green ones, which are 8 in total here, and then the red ones are 9, I think, and then the orange ones are 1 and the yellow ones are 2. So in this case, I got the ones which I got right are 8 plus 9. So, and the ones which I got wrong were 2 plus 1. So the misclassification rate here would just be 3 over 20, which would be the off-diagonal elements divided by the total of elements. That's the misclassification rate. But it can be a bit misleading in some cases, especially if classes are balanced. In this case, the classes are more or less balanced, but in the case of the emails which I mentioned, the classes can be quite often, so the numbers can be very misleading. Now, there are all kinds of names for this errors. Sometimes the false positive are also sometimes called a type 1 error. Type 1, and those ones here, the false negative, are also sometimes called the type 2. Looks a bit, might want to tidy this up a little bit. Oh, now I'm messing it up here. Let's just mark it again. We had green here, red here, orange here, and yellow here. And the yellow ones are sometimes called the type 2. The yellow ones are sometimes called the type 2 error, and the orange ones are sometimes called the type 1 error as well, which is just the different names for marking them. So false positive type 1 and false negative type 2. They can be quite different and they can have quite different impacts. Sometimes, so if you care about misclassification, for example, you just care about the sum. I got 3 out of 20 wrong, but just think about an example. Think about a cancer study. So here we want to predict cancer, and then actually in some cases I get it wrong, but you know, for the false positive, I predicted the person to have cancer and the person actually didn't have cancer. So I got it wrong, but maybe I sent the patient to an exam they didn't need it. It could have cost the NHS a bit more money, but that's about it. Whereas for the false negatives, I predicted the patient to not have cancer. The patient actually had cancer. Maybe this patient went without an exam and died because of this. So the effect of the errors can be quite different. So you saw this error made the patients to die, whereas this one just costs a little bit more money. So they can have quite different effects, and sometimes it's not about getting the smallest misclassification rate, but maybe I want to minimize one of those errors. Maybe I want to minimize this error here. Maybe I want to minimize that error. Maybe I want to balance something. I want to minimize this error, which I could minimize by, say, sending all the patients off to an exam, that I never get it wrong, but then obviously I get many of the other ones wrong, and that will cost a lot of money, maybe too much for the program to be feasible. So I have to find a balance where I kind of strike the best balance, where I can save as much lives but also have a program which is payable. So that is something to keep in mind, and we will talk a little bit about those different errors and how we can, in a sense, control them, and when can we actually say when a model is good, because misclassification rate not necessarily tells me whether the model is good or not, as we have seen in some of these examples. Sometimes good means saving more patients, or sometimes in the case of the emails where I have mislabeled classes, maybe a misclassification rate which is very small might not at all be a smart model. It might just be in that, well, actually it's a trivial model in a kind of very balanced world. So this is something I want to talk about now a bit more. So the first thing is, how can I actually vary this different classes, and one way of dealing with it is this ideas of threshold. For example, here in this case I had this decision boundary in this case of the students which failed the exam or passed the exam, and I set it at a probability of 1/2. Whenever the prediction of them passing was larger than 1/2, I would classify them as pass. But obviously I can vary this value of 1/2 here, and if I vary it, I will shift this line to the right or to the left. For example, if I make it higher, so I have a higher threshold, I only mark those students to pass for which the probability was actually not above 50% but above 90%, then I maybe get this line here, in which case only very few students, like say those two, actually were above this threshold. But if this would be, for example, if I said p equal 0.9, here I have p equal 0.5 or p star, and then I could have a case where p star would be equal to 0.2 or something like this. In this case I have a very low bar. Whenever the lowest bar, I would say, okay, they will already pass. So you see most of the students are to the right of this line. I will predict most of the students to pass, and because I have a very small threshold. So this is important, and this can help us to control some of those errors. We can already see why. Just think about say the spam case, for example. Let's just look at the spam case and say, imagine I value those errors differently. For example, I have a different importance, say, for whether I have an important email and it ends up in my spam filter and I do not see it. That's a very big disturbance for me, because I might have missed some important information. Whereas, for example, if there was a spam email which I received in my inbox by mistake, I can just look at it, delete it, and that's maybe much less of a disturbance than the case where the important email ended up in the spam filter. Maybe I had to pay a bill and I didn't pay the bill because of that. So that might create quite a lot of headache. So I have different values for this different type of errors. Those are the kind of type 1 and type 2 errors, and I value them differently. And I imagine I want to tune my model to make up for this fact, so I can just tune this value. And if I say p star would be the value for ranking it as spam, if I, for example, make this threshold higher, say to 90%, it makes it harder for emails to be ranked as spam. Therefore, it makes it less likely for me to maybe mark an email which wasn't spam mistakenly as spam, but kind of on the flip side, I will also now receive more spam emails in my inbox, and I have to delete them. But if I say it is very important for me that I never miss an important email which ends up in my spam, I will set P star higher than 50%. I will set it, say, to 90% or 80%, and we will talk later a little bit about how I can come up with this value. But if I'd say, well, I don't really care about this, but I'm very annoyed when I get any spam in my email, so I will just lower this value P star to something like, say, 0.2. So this is how I can set the threshold, and this is how I can somehow control those two values here, the kind of false positive and false negatives, the type 1 and type 2, by just basically valuing this thing. This is, say, when I predicted it was spam, but it was actually not spam. This was the important email which ended up in the spam filter, the type 1. So if I kind of, if I care really a lot about this, about the type 1 error, if I want to have it lower, I would have to set the threshold higher. Whereas if I care more about this thing, I would set the threshold lower. So this is one way of kind of setting this threshold and kind of adjusting the those errors. So I hope it makes sense, and that you get a better understanding of how you can actually control this error matrix. But it still leaves us with the open question, like, okay, how do I then actually know how good the model is? If kind of, I already argued that misclassification rate is not necessarily the best measure, which is just the sum of the off diagonals. Then I argued that the individual errors might be more relevant for me, but somehow I can set the threshold and change them all the time. I have the same model, the same prediction. After I fitted the model, all I do is shifting this threshold P star after fitting the model. So it's the same model. The model isn't getting any better or worse, but I can somehow magically shift those errors around. So where shall I then focus on? What is the quantity which actually tells me how good the model is? And there's where the ROC curve, or the receiver operator characteristic, comes in. And that's a very kind of mouthful of a word, but this is how it's called. It comes from engineering science. And another quantity, which is AUM, or area under curve, AUC, area under curve, which is what we also will be talking about. So to do that, I first have to define this receiver operator curve. And to define it, what I plot here, so I look at the same confusion matrix we had earlier, and I will take the true positives, which are those ones here, and I take the false positive, which are those ones, and I will effectively take all the true positive, and I divide it by the sum of all the true variables, which is the sum of those here. And I take the false positive and I divide it by the sum of all those here. So this would be the negative, and I take the false positive divided by all the negative, and I take the true positive and I divide it by all the positives here, which is kind of, so this would be the first entry divided by the sum of the first column, and the second, the false positive rate, would be the top entry of the second column divided by the sum over all the columns. If I do this, I have here the true positive rate, which is defined as true positive over all positive, and the false positive rate defined by the false positive divided by all negatives. Now if I take those two and I plot them one against the other, so I put true positive rate on the y-axis and false positive rate on the x-axis, I plot everything from 0 to 1, then I will get a curve like this. And it's getting a bit messy, so maybe we can kind of redraw this very quickly on the next slide. So let's just kind of copy this information here. So I have true positive, false positive, false negative, and true negative. Okay, then I have the so this is my confusion matrix here. This is what is predicted, and this is what the actual label is. And this is first the positive one, and then the negative one. And the same here, first the positive, and then the negative. And then I have the weights here. I have the true positive weight, which is just the true positive weight, which I just said is true positives, divided by all the positives, which would be true positive, plus false negative. And then I have the other one, which would be the false positive weight, which is just false positive, divided by the sum over the second column, false positive plus true negative. So those are two quantities here, and I plot them here. This is false positive weight, and this is true positive weight, from 0 to 1. Now importantly, if my model is kind of random, if I'm random guessing, I'm getting as many true positives as false positives. So a random guess will always be a 45-degree line here from 0 to the 1 here. So this dashed line will be a random guess, a random model. Now, what would be the best case scenario? The best case scenario is that all my predictions would be correct. So all the true positives would be actual positives there, and then there would be no false positive because I get all of them correct. So in this case, I would have the true positive weight equal to 1 and the false positive weight equal to 0. This would be like the ideal or the best classifier. This would be the best model. So a kind of trivial model is a random model, which is the dashed line, and the best classifier, the ideal model, is the red line. And the reality lies somewhere in between. So my model could look something like this, or maybe then I fitted a new model, I found a better predictor, and I get something like this. You see that the orange model is closer to the ideal classifier, so the models get better as I move upwards. So the random model is the 45-degree line, the green model is a bit better, and the orange model is even better. And one way of measuring it is looking at the area under the curve, this AUC, which is just the whole area under the curve, as the name said. So for example, for the 45-degree line, I would get this area, which given that the line is 45 degree in a 1 by 1, it would just be a half there. Now the red line, I would feel the red line will basically correspond to effectively the idealized this curve here, which in the limit will give me an area of 1. So basically the area under the curve would be a half for the random model and 1 for the ideal classifier. So let me 1 for the ideal, and for the random one, which I wrote in blue, I would get a half there. So this is a good value of summarizing in a single number how good the model is. So it's between 1/2 for the random model and 1 for the ideal model. And my model would be something in between. So if I have one model which is area under the curve of 90%, the other one 92%, the 92% one is better. And this is regardless of the threshold. It's regardless of how much I care about those numbers here. How much do I care about the false positive and the false negative here? It doesn't really depend how much I care and how I choose the threshold. This number will be the same no matter how I choose the threshold. And actually, choosing the threshold, I will obtain this curve. You can see that very easily. So just think a little bit about it. What happened if I set my threshold equal to 1 in the previous case? So if we go back one here, what happens if I set the threshold to not to 1, sorry, to the threshold to 0. If I set the threshold to 0, I will classify everyone as passing there. So effectively, I classify everyone as passing, so I get all the pass correctly. All the green dots will be correctly classified as pass. The other ones will also be classified as pass because I basically shifted P star to 0. So see, this will be the case when the true positive rate is actually equal to 1. So this would be this point here effectively. So I'm here at this point. Now if I tune this value further upwards and upwards and upwards, eventually if it gets closer to 1 P star, I will not classify anyone anymore to pass. I will basically classify everyone as fail as this number approaches 1, and then I would be here in this point. So effectively, as I vary P star from 0 to 1, I will be traveling along this curve here. And this is actually how this curve is obtained. So after you fitted a model, if you want the Python comment to get for you the receiver operator curve, so if you want the comment to get the receiver operator curve, it will effectively just take your model, it will take P star, it will vary it in small increments from 0 to 1, and it will obtain all these points which form the curve. Then you can actually look at the curve, and then the computer can also obtain for you on this kind of discretized level, it can calculate for you the whole area under the curve. So if you want a receiver operator curve analysis and an area under curve calculation in Python, all it does for you is vary this P star and obtain this curve for you. So that's a lot of information here, but I think it is quite useful for you to understand all those relationships, and you will be also better be able to evaluate certain classification problems, because as we said earlier, misclassification error not necessarily is the best value of interest, which would be the sum of the yellow and the orange term here. In some cases you might be interested in just getting the best possible false positive rate or the best possible false negative rate with some constraints in there. Obviously you do not want to say everything is spam and nothing is spam, but you want to have a kind of trade-offs there, and this trade-off obviously involves some cost function here. For example, what does it cost the NHS to see more patients, and what would be the cost if I get a patient kind of slips with a net, and then later his situation becomes worse, and then maybe the operations are much more expensive. So there will be a trade-off, and you often will be able to optimize what is the best threshold which best balances those two cost measures, which kind of define the false positive and the false negative rate. So this is very important for many applications, and I hope this kind of discussions gives you a better understanding. And as I said, that's not just important for logistic regression, but really for any classification setup. It will be applicable also to discriminant analysis, which we will discuss now, but also to other classification models such as support factor classifiers, which we will be discussing next week. But now we will talk first about discriminant analysis.